Usually when we talk about like a medical diagnosis, there is this expectation of absolute precision, right?
Oh, sure. Yeah.
It feels like engineering. You break your arm, the x-ray shows that jagged white line in the radius bone, and the doctor just points to it and says, there it is.
Right. It's very definitive.
Exactly. Broken or not broken. It is a clean binary reality. But then you step into the world of predicting the future state of a chaotic atmosphere, and suddenly, that x-ray machine is broken.
It is entirely broken.
The diagnostic landscape we are looking at is, well, it's fundamentally murky because for decades, the entire meteorological community has relied on these massive physics-based supercomputers to map out the weather, right? Simulating every single fluid dynamic across the globe in this massive act of just brute force calculation.
Yeah, heavy mathematical lifting.
But right now, based on the latest research that has been done, artificial intelligence is fundamentally upending that entire paradigm. Like, we are shifting from pure deterministic physics to probabilistic machine learning. And the implications for the 2026 hurricane season and really just our general understanding of the Earth system are absolutely staggering.
Oh, completely.
Welcome to Meteorology Matters, the podcast that dives deep into the science, chaos, and stories behind the weather that shapes our world. This show was created by meteorologist Rob Jones. Now, let's get into today's episode of Meteorology Matters.
It is great to be here for this.
Welcome, everyone. We have a highly requested analysis today. We are looking closely at how this cutting-edge digital infrastructure is suddenly colliding with raw, chaotic nature. To guide you through the research that has been done, I want to bring in our expert to help us really parse out what this all actually means.
Thanks for having me. And, to start, we are standing at what is probably the most significant inflection point in atmospheric science since the launch of the first weather satellite.
Like TIROS-1 back in the 60s.
Exactly. TIROS-1, for the better part of a century, the way we predicted the weather was essentially this really heavy mathematical exercise.
Mm-hmm.
And now we're entering an era where computational systems simply intuit the weather based on decades of learned patterns.
Which is wild to think about.
It really is. The transition from, calculating physics to recognizing these massive multidimensional patterns, it is a monumental shift in how we understand our planet.
And before we dive into the deep mechanics of how that intuition actually operates, I want to quickly encourage you, the listener, to follow meteorologist Rob Jones. You can find him on Instagram at meteorologist, on TikTok at TV Meteorologist, and on YouTube at Rob Jones Hurricane.
Definitely go check those out.
Yeah, that YouTube channel is the official home for the Meteorology Matters podcast playlist, so make sure to check that out. And please take a second to like, follow, comment, and rate the podcast on whatever platform you use. It genuinely helps keep these deep dive conversations going.
It really does.
So let's get into this paradigm shift. Because to fully grasp the magnitude of this AI revolution, we cannot just look at the new models, right? We have to thoroughly examine the old guard.
Right, the traditional methods.
Traditional forecasting, specifically numerical weather prediction or NWP. I want to break down exactly why generating a forecast the traditional way is such a monumental heavy lift.
Yeah. So if you look at the fundamental architecture of traditional models, like the global forecast system, for example, you have to picture the Earth wrapped in this massive, invisible, three-dimensional mesh grid.
Like a giant wireframe globe.
Exactly. The atmosphere is sliced up into millions of little boxes. Traditional NWP takes the current state of the atmosphere, the temperature, the humidity, the barometric pressure, the wind vectors at thousands of different points from ground level all the way up to the stratosphere. And it maps those initial observations into every single one of those little boxes.
And once the current data is locked in those boxes, the computer has to run the Navier-Stokes equations, right?
Yes, the big ones.
These are the foundational equations describing the motion of viscous fluid substances. It essentially calculates how the air and moisture in box A will physically flow into box B over the next, say, 5 minutes.
And the Navier-Stokes equations are notoriously brutal to solve, especially on a planetary scale. I mean, the computer is actively enforcing the physical laws of conservation of mass, conservation of momentum, and conservation of energy for every single parcel of air.
Wow.
And remember, the atmosphere is a continuously flowing, highly turbulent fluid. To run these calculations for the entire globe, projecting multiple days into the future, it requires processing facilities that literally take up entire warehouses.
Right.
We are talking about the most expensive supercomputers on Earth running quadrillions of calculations per second.
Which is incredible, but I have always found the limitation here totally fascinating because the grid boxes in a global model, they might be roughly 8 or 10 miles wide, right?
Right, depending on the resolution.
But a single thunderstorm or a specific updraft inside a hurricane, that might only be 1 mile wide. So the supercomputer actually cannot see the individual thunderstorm.
Yes, exactly. The concept you were describing there is the parameterization problem.
Yeah.
Because the grid boxes are simply too large to resolve these micro-scale physical processes, like individual cloud formation or even soil evaporation. The physicists have to write separate, highly simplified algorithms to just estimate those effects within the box.
Oh, I see.
So you have the overarching Navier-Stokes equations running the large-scale flow, and then these localized parameterization schemes running simultaneously to sort of guess the behavior of all the small stuff. And coordinating all of that math takes a massive toll. Even with those warehouse-sized supercomputers, it takes hours to generate a single global forecast run.
Hours. Which brings us to the new frontier, right? Artificial intelligence weather prediction. The recent research points to some major players totally upending this process. Specifically, Google DeepMind's GraphCast, their newer model called GenCast, and the AIGEFS model developed by the National Oceanic and Atmospheric Administration.
Yes, the National Oceanic and Atmospheric Administration has been very active here.
I am hung up on one primary concept here, though. If these AI models are skipping the multi-hour physics calculations entirely, how are they actually arriving at a future weather state?
Well, they bypass the fluid dynamics equations by shifting the entire computational burden from the forecast phase to the training phase. The AI methodology relies on massive archival datasets, commonly referred to as reanalysis data.
Reanalysis data.
Right. We are talking about historical datasets spanning 40 or 50 years that contain a comprehensive, mathematically balanced record of the global atmosphere. So the AI is trained on this massive archive. It looks at the global atmospheric state on a Tuesday in 1994, for example, and then it looks at the verified reality of what happened on Wednesday in 1994.
Oh, wow. So it is looking at the initial state and the final state millions and millions of times.
It's millions of times. And through deep learning, the neural network adjusts its internal weights to map the relationship between Tuesday and Wednesday. It learns the deeply complex nonlinear relationships between atmospheric variables over space and time.
So it's making its own connection.
Exactly. It learns how a pressure drop off the coast of Africa interacts with a specific wind shear profile to produce a tropical wave. The machine does not know what the Navier-Stokes equations are. It does not know the laws of thermodynamics.
It has no idea what physics even is.
Not at all. It simply knows that when the atmosphere looks like this, it almost always results in that.
So the AI is recognizing the pattern, not crunching the underlying physical forces. You know, I want to test an analogy here.
Sure, go for it.
Is traditional forecasting like trying to calculate the exact physics of every single bounce in a pinball machine? Like you measure the velocity of the flipper, the friction coefficient of the wood, the angle of the bumpers, the exact mass of the steel ball.
Yeah, calculating all the variables.
Right, whereas the AI is like a seasoned arcade player who just watches a million games of pinball until they intuitively know exactly where the ball will end up just by observing the initial launch.
That is actually a great way to think about it. The seasoned arcade player analogy holds up well, but we do need to refine how the AI actually views the ball, because the AI is not operating deterministically, giving you one definitive final location. It operates probabilistically.
Meaning it says, out of the million games I have watched with this specific launch angle, the ball ends up here 70% of the time and hits a different bumper 30% of the time.
Precisely. That probabilistic output is crucial. And this relates directly to a broader concept highlighted in the research regarding Google DeepMind's philosophy. They are not merely trying to build a faster weather app. They are utilizing meteorology to attack what they term root nodes.
Root nodes. What exactly constitutes a root node in artificial intelligence?
Well, if you visualize the field of AI as a massive tree, the leaves and the small branches are the specific consumer applications. You know, a large language model, writing an email, recommendation algorithm on a streaming service, an image generator.
The stuff we use every day.
Right. The root nodes, however, are the foundational, intractable mathematical problems that form the base of the trunk. DeepMind views the chaotic, highly complex fluid dynamics of global weather as a root node problem.
Oh, I see where this is going.
Yeah, if an artificial neural network can learn to accurately predict the Earth's atmosphere without being explicitly programmed with the laws of physics, the underlying mathematical architecture required to achieve that can be mapped onto countless other fields.
Wait, really? So if you can teach an AI to predict the atmosphere, you can use that same fundamental neural architecture to predict the folding of complex proteins or the fluid dynamics of a fusion reactor.
Exactly. The architecture is transferable. And the research details the underlying technology enabling this kind of deep pattern recognition, specifically focusing on data processing methods like embeddings. Gemini embedding 2 is referenced frequently in the literature. To understand how an AI digests chaotic weather, you have to understand the concept of latent space.
Okay, let's explore that, because I imagine you cannot just feed raw wind speeds and temperature numbers into a neural network and expect it to magically understand a hurricane. How does an embedding actually convert the weather into something the AI can interpret?
So, embedding is a highly sophisticated translation mechanism. It takes complex, real-world information and converts it into unified numerical vectors. Think of a vector as a coordinate in a massive, multidimensional mathematical space.
Okay, a coordinate.
Right. If we were embedding language, concepts that share semantic meaning are placed close together. So the vector for king and the vector for queen would be mathematically adjacent. When you apply this to atmospheric data, the embedding model takes disparate types of information like satellite imagery, surface pressure readings, oceanic heat content, and projects them into this high-dimensional space.
Oh, wow. So it basically creates a mathematical topography of the weather, a specific pressure gradient, and a specific mid-level moisture profile that typically combine to form a supercell thunderstorm are mapped closely together in this vector space.
Yes, the network clusters those atmospheric features. This allows the AI to recognize profound, multivariable patterns across massive datasets that a human meteorologist or even a traditional physics model could never possibly visualize. The AI sees the deep, hidden structural relationships of the weather in a purely mathematical dimension.
That paints a really vivid picture of this highly trained, intuitive system. But, moving from theory to reality is where the friction always happens. How does this new pattern recognition actually perform when lives are on the line in the real world? It is one thing to backtest against a storm from 1994, and another entirely to predict a volatile hurricane forming right now in the Atlantic.
It is a totally different ballgame, yes. But the transition from experimental theory to frontline operational application over the last few years has been startling. The research highlights the massive successes during the 2025 hurricane season as undeniable proof of concept. For example, the Functional Generative Network, or FGN, is a probabilistic AI model that was heavily utilized by the forecasters at the National Hurricane Center.
Yeah, I read the case study and the research regarding Hurricane Lee. GraphCast managed to predict the specific landfall of Hurricane Lee 9 days in advance, 9 days out, and it had the track locked in.
And to contextualize why 9 days is such a paradigm-shifting metric, you have to remember that the traditional multi-million-dollar physics-based models were struggling with the steering currents. They did not catch on to the correct track until roughly day 6.
Wow.
So outperforming the global physics models by 3 critical days is an absolute eternity in emergency management.
It really is. I mean, the logistics of coastal evacuation are massive. 3 days is the difference between an orderly, staged evacuation of a coastal hospital network and a chaotic, gridlocked scramble on the highways.
Exactly. And the early detection was not an isolated fluke. The research details a similar performance with Hurricane Melissa. This was a historic, record-breaking October storm. Late-season storms are notoriously difficult for traditional models to handle because the synoptic setup is in transition.
What do you mean by in transition?
Well, you have summer-like ocean heat interacting with strong, fall-like baroclinic cold fronts coming off the North American continent. The physics models often struggle with the complex energy transfers during those seasonal transitions.
Yet the AI models honed in on both the track and the rapid intensity changes of Hurricane Melissa extremely early. The research noted that the AI guidance was so remarkably consistent that it gave human forecasters the confidence to explicitly predict a Category 5 landfall well before the storm even approached the coast.
Making an explicit forecast for a Category 5 landfall is a massive, highly scrutinized decision. Forecasters simply do not make that call unless their guidance is overwhelmingly confident. The 2025 Atlantic Basin performance graphs included in the research show the Google AI model consistently charting higher than the official forecast and the traditional numerical models.
So it's just better across the board.
It demonstrated a significantly higher skill score relative to the standard baselines for both track placement and intensity prediction.
There is a vital point here that I want to dissect, though. The research references a specific concept regarding why AI is uniquely suited for atmospheric forecasting. Weather is fundamentally chaotic, and therefore we need to understand the tails. What does it mean to focus on the tails of a weather event?
Uh, so, if you plot the possible future tracks of a hurricane on a standard bell curve, the large hump in the middle represents the most likely outcomes, right?
The consensus, essentially.
Exactly. The tapering ends of the curve, the tails, represent the extreme edge cases. In a chaotic system governed by the butterfly effect, a minor, almost imperceptible variation in the starting wind speed can compound over days and push the storm into one of those extreme tail scenarios. Because traditional deterministic physics models take hours to compute, you can only afford the supercomputer time to run them a few dozen times.
So a traditional ensemble forecast might give you, what, 50 possible tracks for the hurricane?
50 tracks give you a decent sense of the middle of the bell curve, but it might completely miss a low-probability, high-impact tail event. By contrast, an AI model like GenCast can generate a 15-day global forecast in just 8 minutes on a single TPU chip.
8 minutes.
Right, because the computational cost is fractions of a penny compared to the physics models, you can run the AI hundreds or even thousands of times, introducing microscopic perturbations to the starting data each time.
So you generate this massive fan of possible tracks. The research actually states that for the 2026 season, the technology allows for 1,000 different tracks to be generated instantly.
Generating 1,000 tracks illuminates the entire probability space. The mean of those 1,000 tracks serves as the official forecast line. But observing the entire spread allows meteorologists to clearly see the tail events.
The outliers.
Right. If 40 out of those 1,000 tracks show the storm undergoing extreme rapid intensification and stalling over a major metropolitan area, you know mathematically there's a 4% chance of a catastrophic edge case scenario. You can communicate that specific risk profile directly to emergency managers.
The efficiency of AI unlocks that massive ensemble approach. But, this raises a massive red flag for me, and it is something the meteorological community is actively grappling with. Are we not risking everything by trusting a black box?
The black box problem, yes.
We are relying on an algorithm that produces 1,000 brilliant tracks, but it cannot necessarily explain its own internal math to us, right?
The interpretability problem is absolutely the most pressing concern in the field right now, and the research addresses it head-on. When a traditional physics model hallucinates a storm that does not exist, or misses a rapid intensification cycle, a dynamicist can open up the code, look at the specific heat flux equations, and see exactly where the fluid dynamics derailed.
You can trace the math.
Exactly. But when a deep learning neural network gets it wrong, diagnosing the specific vector weight that caused the error is incredibly difficult.
So we know it recognized the wrong pattern, but we don't know why it thought the pattern was there. How is the scientific community mitigating that risk?
Well, mitigation is happening on two fronts. First, there is heavy active research into explainable AI, or feature attribution. Scientists are developing secondary algorithms designed to sort of peer inside the black box and map which specific initial input, say a pocket of dry air in the mid-levels, the network heavily prioritized when making its decision.
Okay, that makes sense.
And the second, and honestly far more critical mitigation, is the preservation of the human meteorologist.
The AI does not replace the forecaster.
No, the human expert is the vital synthesizer. They evaluate the traditional physics models, analyze the 1,000 AI tracks, recognize the historical biases inherent in both systems, and formulate a coherent, contextually aware message. You just cannot automate life safety decisions based purely on the uninterpreted output of a black box.
Yeah, that leads perfectly into the next major revelation in the research. Because if AI is incredibly fast and currently dominating the skill charts for hurricane tracks, a lot of people might assume we should just unplug the massive physics supercomputers and save the electricity, right? But
Yeah.
the research points to the exact opposite. We are entering an era of the ultimate team-up.
Yes, the synergy between the two paradigms is where the true revolution lies. The research highlights the stark limitations of artificial intelligence. It is a fundamental law of machine learning. A model is only as robust as the data it has consumed.
Right.
AI shines brilliantly when there is abundant observational data. The atmosphere over North America and Western Europe is heavily instrumented with weather balloons, radar grids, and surface stations. The reanalysis datasets for those regions are incredibly rich.
But the Earth is mostly ocean.
Exactly. And large swaths of the developing world have very sparse observational networks. When an AI is asked to predict the weather in a data-poor region, or more importantly, when it's confronted with an unprecedented climate-warming-driven extreme event that has absolutely no historical analog in its training data, the AI struggles.
Because it hasn't seen it before.
Right. It has never seen the pattern, so it cannot intuit the outcome. In those specific scenarios, traditional physics-based simulations remain superior because they operate on immutable physical laws, the conservation of mass and energy, rather than relying on historical trends.
So machine learning cannot entirely supplant the laws of physics, which brings us to a fascinating, highly specific application of this synergy: coastal engineering and storm surge forecasting.
Oh, this is a great example.
The research details how models like ADCRC are used to predict the devastating wall of water a hurricane pushes onto the coastline. Now, ADCRC is a hardcore traditional physics model, but the research notes it has a problem with systemic errors. Why does a physics model consistently get the water levels wrong in certain areas?
The error stems from the computational impossibility of perfectly simulating a real-world coastline. I mean, a storm surge model has to calculate the physical stress of the wind on the ocean surface, the inverse barometer effect of low pressure sucking the water upward, the wave setup as the surge hits the continental shelf, and the friction of the water flowing into complex estuaries and over wetlands.
That is a lot of math.
It is, and to calculate that perfectly, the model would need an exact sub-meter resolution map of the nearshore bathymetry.
So you would literally need to know the elevation of every sandbar, the exact height of every levee, and the density of the marsh grass.
Yes, which is impossible to map constantly, let alone feed into a fluid dynamics equation. So the physicists have to simplify the coastline into a much coarser mesh grid. Because of that structural simplification, the model develops built-in biases.
Like what?
For example, it might consistently underestimate the storm surge height at a specific tide gauge station inside a bay because the coarse grid does not accurately resolve a narrow inlet that actively funnels and amplifies the incoming water.
Okay, so it is a systemic error. The physics model makes the exact same mathematical mistake in the exact same location every single time a storm approaches from a specific angle.
Exactly. And this is where the researchers introduced a brilliantly elegant solution using LSTM neural networks.
LSTM stands for long short-term memory, right? If we look under the hood of an LSTM, how does a specific architecture differ from a standard neural network?
Well, an LSTM is a highly specialized type of recurrent neural network. Standard neural networks process individual data points independently, but an LSTM is designed to process sequential data, like a time series of rising water levels during a hurricane.
Ah.
The architecture contains internal mechanisms called memory cells, and these are regulated by structures known as input gates, output gates, and forget gates. These mathematical gates allow the network to selectively remember important trends from previous time steps and actively forget irrelevant noise, allowing it to recognize deep temporal patterns.
Wow, okay, so how did the researchers apply this memory network to the storm surge problem? The research states they trained an LSTM model on 61 historical storms that impacted the U.S., South, the Southeast, and the Gulf of Mexico.
The critical distinction here is that they did not train the AI to predict the storm surge from scratch. They trained it to act as a highly specialized post-processing filter on the physics model.
A filter.
Yes. They fed the AI the flawed historical output from the ADCRE physics model, and then alongside it, they fed the AI the actual verified real-world water level observations from those 61 historical storms.
The AI is essentially grading the physics model's homework.
That is exactly what it's doing.
It learns that whenever the physics model predicts a 5-foot surge with a strong southeast wind at a specific dock in the Gulf of Mexico, it is systematically underestimating the water level by 2 feet because of the unresolved bathymetry.
Precisely. The AI maps the aerodynamics of the physics engine. In real-time operations, you run the fast, slightly simplified physics model to get the baseline surge, and then you feed that output through the AI filter. The LSTM applies an instantaneous, highly localized bias correction. When tested on novel storms, this hybrid approach vastly improved forecasting accuracy across the majority of the coastal gauge stations.
There is a finding in the research here that genuinely surprised me, though. The researchers realized during testing that they did not actually need the data from all 61 historical storms to train the AI effectively. They discovered that a highly diverse subset of just 6 hurricanes provided the exact same quality of bias correction. How does an AI achieve maximum accuracy with a fraction of the training data?
It really speaks to the efficiency of the LSTM architecture in capturing the underlying relationship between the storm forcing and the local geography. If those 6 storms represent a highly diverse set of parameters, a fast-moving Category 1, the slow-moving Category 4, different approach angles, different tidal phases, They expose the physics model to a wide enough variety of scenarios for the AI to fully map the spectrum of its systemic errors at that specific location.
Right.
The AI learns how the simplified physics grid interacts with reality so thoroughly that adding data from 55 more storms provides severely diminishing returns.
I am going to play devil's advocate for a moment.
Oh, and
Isn't applying an AI filter just slapping a digital Band-Aid on a flawed physics model? I mean, if we mathematically know the model is wrong because we lack granular bathymetry data, why don't we just mandate better mapping? Why not fix the underlying physics rather than relying on an algorithm to hide the mistakes?
it is a valid philosophical argument, for sure, but it shatters against operational reality. Mapping the constantly shifting bathymetry of the entire Gulf of Mexico and the Atlantic seaboard at a sub-meter resolution is logistically impossible.
Because it's always changing.
Constantly. Every single major winter, nor'easter, or localized hurricane moves millions of tons of sand, instantly rendering the previous bathymetric maps obsolete. Furthermore, even if you possessed a perfect real-time map of every grain of sand, running a Navier-Stokes fluid simulation at that extreme resolution would take days to process. The actual storm surge would destroy the coastline before the supercomputer finished running the forecast.
Oh, wow. So the computational cost of perfection is just way too high.
Way too high. The bias correction is an elegant, highly transferable, and computationally cheap workaround. You run the slightly simplified physics model, which completes its run quickly, and then apply the pre-trained machine learning filter, which executes the corrections in milliseconds.
Best of both worlds.
Exactly. You achieve the operational accuracy of a hypergranular physics simulation without the devastating computational latency. It is the perfect marriage of raw physics and adaptive machine learning.
With this incredibly powerful arsenal of hybrid models coming online, we really have to look at what these systems are actually showing us for the immediate future. Based on the research, what is the 2026 horizon looking like? What are the underlying atmospheric drivers for the upcoming hurricane season?
Well, the defining meteorological feature looming over the entire 2026 global weather pattern is a developing El Niño.
We hear the term El Niño constantly in the media, but the physical mechanisms are rarely explained. Let's break down the actual thermodynamics here. What precisely is an El Niño, and why does an event in the Pacific dictate the weather in the Atlantic?
Good question. So the mechanism centers on a massive region of the equatorial Pacific Ocean, specifically south of Hawaii. During an El Niño, the prevailing trade winds that normally push warm surface water toward Asia begin to weaken, or sometimes even reverse.
Okay, so the wind stops pushing the warm water away.
Right, and this allows a massive pool of exceptionally warm water to slide eastward back toward South America. When the sea surface temperatures in this specific region become significantly warmer than the historical average, it radically alters the global atmospheric circulation.
Because that massive pool of warm water acts as a heat engine, right? It increases the evaporation rate, pumping massive amounts of latent heat and moisture directly into the overlying atmosphere.
Yes, the latent heat release drives massive, towering thunderstorms over the central and eastern Pacific. As that heated, buoyant air rises to the top of the troposphere, it hits the stratosphere, which acts like a physical lid. The air diverges and spreads out. A massive volume of that exhaust air is caught in the upper-level westerlies and travels thousands of miles eastward, high above the Earth, until it reaches the tropical Atlantic basin.
And according to the principles of the Hadley cell circulation, what goes up in the Pacific must eventually come down.
Exactly. The upper-level air mass descends over the tropical Atlantic Ocean and the Caribbean Sea. When an air mass descends, two critical things happen. First, the air compresses, warms, and dries out, creating a hostile, stable environment that suppresses the upward convection necessary for a hurricane to form.
Right.
Second, the fast-moving upper-level winds create massive amounts of vertical wind shear over the Atlantic.
Because the wind is blowing at, say, 10 miles per hour at the surface, but 80 miles per hour at the top of the troposphere. So if a hurricane tries to build its vertical vortex, that shear essentially decapitates the storm.
Exactly. And El Niño places a giant, dry, highly sheared atmospheric lid over the Atlantic basin, which is actively hostile to tropical cyclone formation.
And based on this dampening effect, the preliminary seasonal forecast from Colorado State University is projecting slightly below normal hurricane activity for the Atlantic this year. The global models are showing consensus on the El Niño developing, but the research points to a massive immediate wildcard playing out on the other side of the planet, Super Typhoon Sinlaku.
Yes. Sinlaku is a perfect example of how hyperlocal events feed into global teleconnections. It is currently a monster storm in the western Pacific, packing winds equivalent to a strong Category 4 or Category 5 hurricane operating near the U.S. territories of Saipan and Guam.
How does a typhoon spinning 8,000 miles away alter the trajectory of the Atlantic hurricane season? I mean, that seems so disconnected.
It comes back to the trade winds we just discussed. A super typhoon like Sinlaku has a massive, violent circulation. The winds on the bottom half of the storm's vortex are blowing fiercely from west to east. We refer to these as west wind bursts.
West wind bursts. Okay.
These intense winds act like a physical plow on the surface of the Pacific Ocean. They literally push warm surface water and massive oceanic wave energy. Specifically, downwelling Kelvin waves eastward along the equator, directly into the El Niño monitoring region.
Wait, so the typhoon is actively fueling the formation of the El Niño?
It is cementing the broader atmospheric pattern. The west wind bursts accelerate the depression of the oceanic thermocline in the eastern Pacific, ensuring the El Niño locks in and potentially increasing its overall magnitude. A localized storm near Guam is directly reinforcing the atmospheric lid over the Gulf of Mexico.
That is just incredible. The research also tackles the evolving complexity of forecasting future hurricane trends beyond just this single season, and it highlights a fascinating thermodynamic conflict driven by climate warming. Predicting the overall frequency of these storms is getting significantly harder because two massive variables are actively pulling in opposite directions.
Yes, this is a huge area of study.
The variables are potential intensity and the moist entropy deficit. Let's examine the physics behind potential intensity first.
So you can view a hurricane as a massive, natural Carnot heat engine. It extracts heat energy from the warm ocean surface and converts it into kinetic wind energy. Potential intensity is a thermodynamic calculation of the absolute maximum theoretical wind speed a storm could achieve in a given environment, based on the temperature difference between the hot ocean surface and the cold upper atmosphere.
Makes sense.
Under climate warming, as the upper layers of the ocean absorb massive amounts of excess heat, the potential intensity is globally increasing. The environment is becoming primed for stronger, more violent storms.
The ocean is basically a larger, more fully charged battery. But the opposing force, the moist entropy deficit, is actively fighting that potential, right?
Yes, the moist entropy deficit is a metric of the moisture content in the middle layer of the troposphere. A high deficit means the mid-levels are exceptionally dry. Tropical cyclones are incredibly sensitive to dry air. If dry air is entrained into the circulation of a developing hurricane, it creates cold downdrafts that choke off the inflow of warm, moist air, essentially killing the storm's heat engine.
The surprising element in the research is that under global climate warming, while the oceans are undeniably getting hotter, the mid-atmosphere is actually projected to get drier. The moist entropy deficit is increasing.
Right. Historically, in the Atlantic Basin, these two variables generally trended in tandem. Favorable oceans usually meant favorable atmospheric moisture. But the climate models indicate these variables are diverging. The ocean temperatures are screaming for storm formation, while the drying mid-atmosphere is actively suppressing it.
So they are fighting each other.
Exactly. Because of these deeply conflicting signals, predicting the sheer number of tropical cyclones in future decades is mathematically treacherous.
It makes our seasonal forecasts incredibly fragile. So let me pose a direct question on behalf of everyone listening who lives near the coast.
Sure.
If the Colorado state forecast says below normal because the El Niño shear is supposed to protect us, does that mean residents can relax this year? Can people forgo the hurricane shutters and the evacuation plans?
A firm, unequivocal no. That is the most dangerous misconception in seasonal forecasting. A suppressed season overall does not equate to a zero-risk season locally. The atmospheric pattern might be hostile to storms for 90% of the summer, but the atmosphere is fluid.
Right. Things change.
If the wind shear relaxes for just 1 week, and the mid-level moisture aligns perfectly over the incredibly warm waters of the Gulf of Mexico, a storm will form, and it will explosively intensify.
The classic historical precedent for this is 1992.
Yes, 1992 was a notoriously quiet, below-average season due to an El Niño. But that quiet season produced Hurricane Andrew, which leveled South Florida as a catastrophic Category 5. The macro-level forecast of a below-average season provides absolutely zero physical protection if the one major storm of the year tracks over your roof. Global statistics are meaningless when local risk materializes.
The necessity of understanding local risk brings us to the final massive theme in the research. To feed these hungry AI models and to accurately map the thermodynamics of El Niño, we need an immense amount of highly precise observational data.
It all comes down to data.
Exactly. Meteorology isn't just about tracking massive cinematic hurricanes from space. It is deeply reliant on hyperlocal, interconnected environmental data gathered on the ground. I want to shift our focus to the data ecosystem because the research provided several incredible deep dives into how we gather, interpret, and sometimes misinterpret this local data.
Yeah, let's get into it.
Let's begin with urban heat. It seems incredibly straightforward. You place a thermometer in a city and record the temperature. But the research highlights an extensive intercomparison study conducted in the Czech Republic that proves we might be fundamentally misunderstanding urban microclimates.
Gathering accurate temperature data in an urban environment is remarkably difficult.
Yeah.
You cannot simply expose a meteorological sensor to the open air. If direct sunlight hits the metallic probe, the sun heats the metal, and you end up measuring the temperature of the instrument itself rather than the ambient air temperature. To prevent this, sensors are housed inside radiation shields.
These are the white louvered boxes you see attached to weather stations, designed to block the sun but allow the wind to flow through, right?
Yes. But the Czech study revealed that in complex urban settings, the physical shields themselves actively corrupt the data. A city is an extreme thermal environment. Concrete and asphalt have low albedo, meaning they absorb massive amounts of solar radiation and re-emit it as sensible heat long into the night.
Yeah, cities are just heat sinks.
Exactly. Sunlight is reflecting off glass buildings from multiple angles simultaneously. The study found that the material composition of the radiation shield interacts with this multidirectional thermal radiation. Under many standard PVC or older plastic shields, the trapped heat was causing the sensors to significantly overestimate daytime high temperatures and dangerously underestimate warm nighttime temperatures.
Underestimating the nighttime temperature is a critical public health failure. I mean, warm nights are when the human body is physiologically supposed to recover from daytime heat stress. If the sensor data tells city officials that the temperature dropped to a safe level, but the reality on the street is 5 degrees hotter, emergency services are operating blind.
The research concluded that utilizing specifically designed UV-stable white plastic shields is mandatory for accurate readings in these highly reflective environments. The UV-stable material resists the degradation that alters the thermal properties of standard plastics over time. And gathering this highly accurate temperature and humidity data is a prerequisite for calculating the heat index, which the research notes is undergoing a vital scientific overhaul.
The old algorithm for calculating the heat index was notoriously complex and computationally slow. The new algorithm is streamlined, resolves mathematical inconsistencies in extreme heat scenarios, and introduces a sobering new physiological framework for communicating heat stress.
The new terminology represents a massive leap in how we communicate the physiological reality of the weather. Previously, the medical and meteorological communities often used the vague term uncompensable heat to describe extreme conditions. The new framework strictly categorizes the environment based on human physiological limits.
How so?
They define conditions as normothermic when the heat and humidity are oppressive, but a healthy human body can still compensate and maintain a stable core temperature through active sweating and behavioral modification.
The body's natural evaporative cooling engine is still functioning.
Right. The next critical threshold is hyperthermic. In these conditions, the ambient heat and humidity overwhelm the body's cooling mechanisms. Sweating is no longer evaporating effectively. The core temperature begins to actively rise.
That sounds incredibly dangerous.
However, in a hyperthermic state, the body eventually reaches a new equilibrium where the excess heat is radiated away to the environment without fatal consequences, assuming the exposure is limited. It is a dangerous, highly stressful state, but it stabilizes.
And the most extreme classification.
The final category is brutally straightforward, lethal. This defines a thermodynamic environment where the body absolutely cannot cool itself, the core temperature rises uncontrollably, and survival without immediate, intensive medical intervention is physiologically impossible. Deploying these precise terms, backed by uncorrupted data from properly shielded urban sensors, changes the heat index from a vague discomfort metric into a highly actionable public health warning.
Transitioning from the threat of urban heat, the research also explored another hyperlocal hazard that requires massive data synthesis: landslides. Specifically, it examined the secondary impacts of Hurricane Helene in the mountainous terrain of the inland United States. Landslides are incredibly difficult to forecast because they require merging atmospheric data with complex geology.
Yeah, predicting a landslide requires understanding soil mechanics, specifically pore water pressure. When massive amounts of rain infiltrate a steep slope, the water fills the spaces between the soil particles. The pressure pushes the soil grains apart, reducing the internal friction that holds the mountain together until gravity induces a catastrophic failure.
The research evaluated the global LHASA system, the landslide hazard assessment for situational awareness. How accurately did the global LHASA system predict the terrain failures during Hurricane Helene?
In real-time operations, prior to the storm's impact, the LHASA system successfully flagged 57% of the precise locations where catastrophic landslides ultimately occurred. That is a robust baseline. But the true breakthrough in the study came during a post-storm hindcast experiment.
What did they change?
Researchers went back and fed the LHASA system entirely different rainfall data. Instead of using standard global precipitation estimates, they fed it data from the HRRR model, the high-resolution rapid refresh model.
Oh, the HRR model is a localized, rapidly updating forecast that predicts specific thunderstorm tracks and intense rainfall rates down to a 3-kilometer grid.
Exactly. By replacing the coarse global rainfall data with the hypergranular HRRR data, the accuracy of the landslide predictions skyrocketed. It demonstrates a fundamental truth of modern meteorology. Analytical models like LASA are incredibly sophisticated, but their output is entirely bounded by the resolution of their input.
Garbage in, garbage out, basically.
Right. As our localized precipitation forecasts become more precise, especially as AI begins generating hyperlocal rainfall patterns, our ability to warn isolated mountain communities about impending slope failures will improve drastically.
Speaking of the necessity for ground-level truth, let's examine the research regarding tornado intensity estimation. Traditionally, the National Weather Service deploys human survey teams after a tornado strikes. The meteorologists walk through the destruction, examine the structural failure of houses, whether a roof was lifted or exterior walls collapsed, and use those visual damage indicators to estimate the maximum wind speed and assign an EF rating. But there is a massive observational blind spot in that methodology. What happens when a mile-wide tornado tracks across an empty agricultural field with no houses to destroy?
The structural damage methodology inherently biases tornado climatology. A massive, violently rotating vortex might tear through an empty prairie, but because it only hit grass and a few fence posts, the human surveyors are forced to assign it a low EF rating. The true intensity of the storm is lost to history.
That makes sense.
But the research highlights a brilliant new technique utilizing the physics of the debris field itself, specifically looking at cycloidal debris swaths.
A cycloidal debris swath sounds incredibly complex. What physical process creates this pattern on the ground?
If you fly over the path of a powerful tornado that has crossed a relatively flat agricultural area, like a dense cornfield, you will often see distinct, overlapping, loop-like patterns carved into the vegetation. These are the cycloidal swaths. They are created by the complex vortex dynamics at the very base of the funnel.
Multiple vortices.
Yes. You have multiple smaller subvortices rotating violently around the main center of the tornado. As these subvortices interact with the forward motion of the entire storm system, they snap the vegetation and deposit the debris in these mathematically precise looping arcs.
Wow, so the geometry of those loops must be directly tied to the rotational velocity of the subvortices.
Exactly. Using modern high-resolution aerial imagery, drones, and advanced GIS photogrammetry, researchers can map the geometry of these loops with sub-meter precision. By measuring the distance between the consecutive arcs and the overall width of the swath, physicists can mathematically reverse engineer the precise surface wind speed of the tornado.
It's amazing.
It provides an objective, purely physical metric for determining the storm's intensity, completely uncoupled from the arbitrary presence of human infrastructure.
It is utilizing the scars on the Earth as a natural anemometer. From the hyperviolent dynamics of a tornado, the research pivots to a much slower but vastly more expansive environmental crisis: drought. The study analyzed a major infrastructure upgrade in the upper Missouri River Basin, detailing the expansion of the soil moisture monitoring network from a sparse 78 stations to a dense grid of 540 stations. Why is granular soil moisture data so critical that we are deploying hundreds of new sensors?
The deployment is driven by the severe economic reality of the agricultural sector. The research focused on the devastating 2017 flash drought in that region. During that event, the severe lack of soil moisture triggered nearly $200 million in relief payouts to ranchers from the USDA's Livestock Forage Disaster Program. The financial compensation a farmer receives is directly dictated by the severity of the drought mapped in their specific county.
So if the data network is sparse, a farmer's land might be incredibly dry, but the nearest sensor, 50 miles away, might have caught a stray thunderstorm, skewing the interpolation and disqualifying the farmer from financial relief.
That is the exact problem. The researchers ran a simulation of the 2017 drought, but artificially integrated the data that the 540 newly installed stations would have provided. The analysis proved that the vastly improved data density would have reduced the interpolation errors in the drought mapping by more than 20%.
That is a massive improvement.
By accurately mapping the precise boundaries of the soil moisture deficits using time domain reflectometry probes, the system ensures that thousands of farmers who were wrongly excluded from the disaster zone due to coarse data mapping receive the millions of dollars in federal relief they desperately need to survive.
The data dictates the economics, but the implications of drought monitoring extend far beyond agriculture. The research highlighted profound ecological impacts as well, specifically focusing on a study concerning native pollinators.
Yes, the study tracked populations of bees within the genus Bombus, commonly known as bumblebees. The researchers found that bumblebees are exceptionally sensitive to environmental drought conditions, exhibiting much higher mortality and population decline compared to other bee species. But the most vital revelation in the study was how the ecological impact of the drought varied radically depending on the specific ecoregion being monitored.
The macro-level drought did not produce a uniform micro-level impact.
The environmental context governed the outcome. In the Central Appalachians, an ecoregion characterized by dense, contiguous forest cover, slight increases in drought indicators were surprisingly correlated with an increase in bumblebee abundance.
Wait, really? An increase?
Yes, the theory is that the reduced cloud cover during mild drought allows more sunlight to reach the forest floor, stimulating specific floral blooms that the bees rely on.
But the outcome was entirely different in the neighboring ecoregion, right?
In the southern Piedmont, which is a fragmented landscape of urban development, agriculture, and sparse forests, the exact same macro-level drought conditions produced a strong negative impact, actively suppressing the bumblebee populations. The fragmented landscape lacks the deep soil moisture reserves and shaded microclimates of the deep forest, exposing the bees to acute thermal stress and floral desiccation.
So it all comes down to the local environment.
Exactly. It proves that we cannot apply blanket ecological assumptions based on global climate models. We must possess hyper-local environmental monitoring to understand how changing weather patterns are dismantling or temporarily aiding vital ecosystems on a county-by-county level.
The necessity of localized data requires a global commitment to observation. And the research brought up a massive systemic failure in global observation regarding lightning fatalities.
The lightning research highlights a severe lack of observational equity in atmospheric science. The data clearly shows that African nations experience the highest per capita fatalities and severe injuries from lightning strikes of any continent on Earth. The convective thunderstorms over the Congo Basin are some of the most electrically active and violent systems on the planet.
Yet the research notes that despite this horrific human toll, the deployment of lightning detection networks, the funding for meteorological research, and the implementation of basic public safety initiatives in Africa lag drastically behind the resources poured into North America and Europe.
It is a critical blind spot for the international scientific community. The high-resolution data networks we just discussed, the soil moisture probes, the weather radars, the AI supercomputers, they are heavily concentrated in the developed world. To truly understand the global atmospheric system and to protect vulnerable populations, the research funding and the observational hardware must be deployed equitably, targeting the regions experiencing the highest mortality rather than just the regions with the deepest pockets.
Addressing that inequity requires massive international coordination, which leads into the final point from the data ecosystem research: the role of national legislation in driving global environmental standards. The study examined the specific teleconnections between domestic climate legislation and global green development.
The findings were nuanced and very revealing. Implementing strict climate legislation does actively encourage a broader transition to green infrastructure development. However, the study found the impact is profoundly bifurcated.
Meaning what?
The legislation is highly effective in stable, developed nations that already possess the bureaucratic infrastructure to enforce environmental standards. Having a strict pollution law on the books only alters behavior if a well-funded government agency, like the EPA here in the United States, is empowered to actively enforce those protections, levy fines, and negotiate international supply chain standards.
The legislation requires teeth.
Yes, In rapidly developing nations experiencing explosive, unregulated economic growth, the research found the link between climate legislation and actual eco-conscious development is incredibly weak. The sheer momentum of the economic engine simply outpaces the government's capability or willingness to enforce the environmental regulations they have signed into law.
We have covered an immense amount of scientific ground today. We started with the global multidimensional algorithms of Google DeepMind, drilled down into the mathematical biases of coastal storm surge models, examined the thermodynamics of El Nino, and ended up discussing the molecular composition of radiation shields and the microclimates of bumblebees. To synthesize all of this, if I can bring back the technology analogies, it feels like this entire data ecosystem is the equivalent of upgrading a massive display from standard definition to ultra-high definition 4K.
That is a great way to summarize it.
Right. The artificial intelligence models, GraphCast, GenCast, they are the brilliant new processors, but the processor is useless without the pixels. The accuracy of the AI is entirely dependent on the hyper-local physical sensor data feeding into it.
The macro-level pattern recognition of artificial intelligence is fundamentally anchored to the micro-level physics of the environmental sensors. We are watching meteorology rapidly evolve into a unified, entirely digital science, where the localized temperature of an urban street is instantaneously integrated into the global mathematical architecture of the atmosphere.
As we wrap up this deep dive into the research, I want to leave the listener with a final thought on where this is ultimately heading. If AI has already mastered the probabilistic patterns of the weather and is currently outperforming the traditional physics supercomputers in tracking hurricanes, what is the next frontier? Once the AI perfectly predicts the weather, what does it do next?
The final, highly provocative concept emerging from the research involves looking at what these major tech companies are developing outside the strict boundaries of meteorology. They are moving rapidly beyond passive forecasting and pushing into active, three-dimensional world generation.
Generating a world. What does that actually mean in a scientific context? Are we talking about virtual reality?
Consider projects like DeepMind's Genie or Tencent's recent HY World 2.0 model. These are advanced AI systems that can generate consistent, highly interactive, continuously evolving 3D environments based on simple prompts. They're not merely rendering an image or an animation, they're generating a persistent digital reality that inherently understands the rules of physics, object permanence, scale, and fluid collision, simply by having ingested billions of hours of video data.
So if you fuse that generative 3D capability with the meteorological AI we have been discussing,
The implications are staggering. If an AI system can generate a perfectly consistent, interactive 3D environment that inherently obeys the laws of thermodynamics and fluid dynamics, the future of meteorology might not involve running numbers on a 2D mesh grid at all. We are moving toward the creation of a perfect, real-time digital twin of the Earth, a persistent virtual world continuously updated by the millions of soil sensors, weather balloons, and satellites we just discussed.
wow.
In the near future, a meteorologist might not look at a chart of mathematical probabilities. They might simply put on a spatial headset, step inside the digital twin of the atmosphere, and physically watch where the digital rain is falling to know exactly what will happen in the physical world tomorrow. We are transitioning from simulating the math to generating the reality.
From the era of scientists calculating fluid dynamics on a chalkboard to the reality of walking inside the digital twin of a Category 5 hurricane before it even forms. The scope of this scientific evolution is truly difficult to comprehend.
It has been a fascinating discussion.
We have explored a massive amount of research today, and I hope this comprehensive analysis provides you with a profound new understanding of the science, the chaos, and the computational brilliance operating right above our heads. Before you go, please take a moment to rate, comment, and follow the podcast on whatever platform you are currently using. And do not forget to check out meteorologist Rob Jones on Instagram @meteorologist, on TikTok @TV Meteorologist, and on YouTube @RobJonesHurricane. You've been listening to Meteorology Matters, created by meteorologist Rob Jones. Thanks for listening, and remember, meteorology always matters.